Mm. So voltage stability is not as hard as small signal stability or transient stability. So the tools can be simpler. So it won't take many lectures. So it will be only just today and next Tuesday. Next Tuesday will be our last lecture. So if you work for any power company or do some research for power systems, and if you want to address some stability issues, I would see maybe 80% of stability issues will be voltage stability issues, not the small signal stability or transient stability problem. Because the small signal stability and transient stability problem are mainly caused by designs. So if your system has good damping, or you place power system stabilizer to improve the damping, you won't see many oscillation. Even there's oscillation, but they can be quickly damped. Only when the system is very weak, you lose a lot of lines and the new structure is not studied well. You may have small signal stability problem. Transient stability problem can be similar. Today's system can hardly have any transient stability problem. Unless the last stage of something like a cascading failures, you have many outages propagating on the system. Eventually, some generators will become out of step. But usually by single contingency, which happens based on the current condition, normal condition is hardly to have any transient stability. Okay. But voltage stability problems are very different. So it's essentially not a dynamic problem. It's mainly like more like a steady state problem or static problem. But it can only happen on nonlinear system. It won't happen on any linear system. So by this section, we're going to cover some basic concept. First, we'll talk about the voltage collapse versus voltage instability, but they are very related terminology, but they have slight differences. And then we'll introduce the two very useful tools you'll be using at utility companies or work for power industry to study the voltage stability and control. And then we'll talk a little bit about the math from the nonlinear system point of view to understand the mechanism and the voltage instability. So there are two types of issues. Usually, you may still recall there's one slide at the beginning of this class. I show starting from very detailed model, including differential equation, algebra equation, so that can study the nonlinear dynamic of the system. If you use a linearized model, that issue will be small signal stability problem. If you only focus on the differential equation of the nonlinear system, even you can simplify some equation that help you to understand a transient stability problem, similar to like single machine infinity bar system. But if you only focus on how the operating point is moving until the system cannot sustain at that operating point, so you can only use algebra equation based on power flow to study that problem. That fall into the voltage stability problem. So that problem is caused by bifurcations. So there are two types of bifurcations. Each one can cause voltage instability. So I will connect each type of bifurcation to a practical phenomena you may see in the real power system. Then I will talk about some very useful analysis for power grids, not just for very simple system, which is modal analysis. Modal analysis, the method is very similar to the modal analysis we have learned from for the small signal stability problem. But for small signal stability problem, that's about dynamics of a generator. So we use Jacobian for the ordinary differential equation to get the Jacobian matrix A. But here, we're going to get Jacobian not from the dynamic model, from the power flow model. So we study the Jacobian of that power flow model, and based on eigenvalues, we can develop some criterion for voltage stability issue. Then I would briefly talk about a useful tool, which is continuation power flow, which is very useful to calculate the voltage stability limit and margin. Then I'll talk about some causes or preventions of the voltage instabilities. So there are some references. I won't cover all of them, but they are very useful references. So if you want to work on any voltage stability related problems in your dissertations, I strongly recommend you take a look at those references. So first, let's take a look at what happened during a voltage instability event, which is called a voltage collapse. So this is a famous voltage collapse event. It caused a voltage collapse in the late stage of some cascading process. So it happened on July 2nd, 1996, in the Western connection. So you may not familiar with those locations, but actually we mentioned some color. So this is like California, Oregon intertie. So this is a very famous intertie that caused a lot of stability issues. So in 1996, August 10, there's a oscillation happening on the intertie that caused by another cascading failure event. So this is the same year. That's 1 month early than that oscillation event. In that event, in August event, there's oscillation across this intertie, then which caused the collapse of the entire system into 4 to 5 islands. Then there's a blackout of the Western interconnection. The 1 month earlier than that oscillation event, there was a voltage collapse event. So this is like boundary substation between the California state and Oregon state. So you can imagine, so to the north of this intertie that's operated by BPA, a power company. And this red region is a load center. It has a lot of load. And the power is mainly supported by this power plant with 4 generating units. And there's a local generating unit and another transmission path sending some power. But there's not much generation inside of this area. So on that day, so if you measure how the voltage change cause that transmission corridor, mainly you will focus on that substation, which is called Boyce substation. So you can measure the voltage magnitude. So that substation is a 230 kV substation. So voltage should be around 230 kV. So here is like normal voltage, 230. After some event, then so the voltage will change, and eventually the voltage declined very quickly. It become out of control. So let's see what happened. I think this plot draw about, because this is like a 2 o'clock, 24 minutes, 37 seconds. So this is the end of the time is 2 o'clock, 25 minutes, 07 seconds. So this plot describes what happened in 20 to 30 seconds. If I'm correct, yes. Okay. So first event is just a short circuit due to some tree contact and also some relay misoperation. And that shouldn't trip those 2 main line, transmission lines, sending power from the power plant to the load center. But there are 4 lines, 2 of them are actually open. 3 lines, 2 of them are open. Okay. So then the power from this power plant to the load center is was largely impacted. Then it calls some special protection system, which try to protect the generators. So that power plant lost 1 gigawatt load, 1 gigawatt generation. So that largely increased the line flow from the north region, and that make that line almost overloaded. So usually on each transmission line, there are protection. The protection is just try to calculate the apparent impedance based on the local voltage divided by local current. Okay, so if you have a short circuit on that line, so the voltage divided by the local current can be very small. So you know there's a short circuit. But sometimes if the voltage divided by current not that small, there's a possibility the short circuit not happen on this line, but is happening on neighboring line. So you can set up maybe delay time, which means the voltage divided by the current, the measured impedance is suddenly dropped to very low value. That's all trip the line, but it's not that low, but take some time. So you may assume you wait until the protection on that line to trip. But if that line that protection fail, you can trip. So that's called a zone 2 relay. And some transmission line also have zone 3 relay, which is like your neighbor's neighbor. So if your neighbor's neighbor has some short circuit, but your neighbor doesn't trip, and your neighbor doesn't trip, then you need to trip. You need to wait for some time. But when system is operated at highly loaded condition, it can be very tricky to differentiate the real short circuit versus overloaded condition. So this relay, this zone 3 relay, actually misoperated, tripped the line. It believed there's some short circuit in that area, so it tripped the line. So that become almost the only transmission path sending power to this area, but that one is also open. So that all that happened in several seconds, right? So the 4 events. The next one that make this generator to be overloaded. So that generator is tripped. And there's another line is overloaded, become another zone 3 relay trip. So now you have after the 7th or 8th event happened, the voltage quickly dropped to very low value. So here is a 120 kV. So voltage suddenly dropped to about 50 to 60% of the normal voltage. Then the voltage collapse happened. Okay, so there are more lines open, and finally, this California Oregon intertie also open. Then the entire area became in the blackout. So that the entire process happened in just maybe half minutes. All right, so there's no aware oscillation on the system because it's not caused by transient stability or like undamped generator oscillations. It mainly caused by a load area gradually loses the generation from outside, from internal, and then become weaker and weaker. Finally, the voltage cannot be supported. Okay, so on the second day, on next day, which is July 3rd, a similar chain of events occurred, and which caused voltage level in the same area to decline. But because the operator already learned the lessons from the previous day, so the power company is Idaho Power Company. So the system operator immediately took some action to shed load in this area, basically just disconnect some unimportant load. So that helped support voltage in this area. And the system is recovered just in one hour. But for this event, it takes much longer time. It's really a huge blackout in that area. So those 2 events, the first one is really blackout. The second is very good success story to save the system by noticing the potential voltage instability and taking some correct correction. But those 2 events show the importance of a system operator situational awareness. So if the operator knows what's happening on the system and take some quick action, that can save system, can reduce a lot of loss. But the question will be, how can we predict this quick voltage collapse, right? If we draw a line, which is the orange line, so that line indicates 90% of a normal voltage. 90% voltage sounds not good, but not too bad because most of transmission line, they can operate around maybe 95%. For some unimportant line, it's okay to temporarily operate at 93, 92. So 0.9 is not bad, right? Because you can see sometimes the voltage temporarily much higher than 0.9 per unit. Okay, so if you're operator, you have the operating guys saying this system need to operate way above 90%, 0.9, and you use that threshold. And whenever the voltage drop and take action, that's too late. Okay, which means there must be some mechanism behind this phenomenon, showing when the voltage instability can become very likely on your system. Then you need to take some early contraction. That's what we want to answer by this section. So this is very typical voltage instability or voltage collapse problem. So voltage collapse mainly describe what's happening on the system based on the phenomenon. So voltage stay near the normal voltage, but suddenly just drop in a way that cannot be controlled. And there's not a very clear precursor signal or early signal you can predict without knowing what's happening on the system. So we have to use the method for voltage stability analysis to really figure out what happened. Then we can develop some indicator for the problem. We showed this picture before in the first session when we quickly go through all the stability problems. This picture is a very good example to give you ideas on the differences between voltage stability and angle stability or rotary angle stability. Okay, angle stability may include both small signal stability and transient stability, depending on which model you are using. So angle stability usually happens on some single small generator connected to the large system. So this you can utilize a single machine infinite bus system, right, to model this system. And based on the power angle curve, we can use equal area criterion to study the angle stability. Voltage stability happens with a load area connected to a large system through a long transmission. And there's not much local generation to support the load. You have to utilize the tie line flow from the remote area. Okay, to study angle stability, we can use power angle curve. On the power angle curve, so if we study small disturbance, we can linearize the power angle curve at equilibrium. For example, we use this straight line, so that will be, we can calculate synchronizing torque and damping torque, right, to study small signal stability. But for large disturbance, we can compare the A1 and A2, the accelerating area and the decelerating area. And also there's a maximal power you can deliver from the generator to the system. That's called the steady state stability limit. So that one is related to Pmax. But on voltage stability, we study how the voltage change with the power. So when the power increase, the voltage can decline. So what happened here is suddenly when the operating point passes this critical point, and there's no way you can bring the voltage back unless you want to do very aggressive control like load shedding or maybe some other emergency control to save the voltage. So it will be using a different curve. So we're going to talk about this curve. So voltage stability concerns the ability of a power system to maintain acceptable voltages at all buses under normal conditions and following a disturbance. A system enters a state of voltage instability when a disturbance such as an increase in load demand or a change of the system condition causes a progressive and controllable decline in voltage, referred to as voltage collapse. So voltage collapse is a phenomenon, but what happened here is really related to voltage instability. The main factor causing instability of voltage is basically the inability of a power system to meet the demand for reactive power. Later we'll explain why having reactive power that can effectively prevent voltage collapse. And voltage stability problem typically occurs in heavily loaded area or along stress transmission paths when the power transfer margin is insufficient. So to study voltage stability problem, you don't really have very detailed generator model. For some system, you don't need to model generator at all. Right? That's why power flow equation may be enough. What we need is a topology near that load area. Then we try to develop that PV curve. And based on that PV curve, that can tell us when the voltage collapse can happen. Okay. Definitely in many real cases, we also need to consider dynamics. Then we'll need the dynamic model. Let's use this simple system to understand how voltage instability can happen. Basically, we want to figure out how the voltage at load bus. So this load bus is basically just connected to a constant impedance load. Okay, this impedance can change. When the impedance decreases, the load will increase for normal conditions. So we study how this voltage magnitude will change with this active power. First, we can calculate the current. This is absolute current, which is the magnitude of current, which is equal to the voltage of the source divided by the total impedance. Then we get absolute value. Because this formula to comply, we can define a function, a nonlinear function of the load impedance. So the current will be equal to some factor multiplying this one. So this one has later we'll see this one has meaning of short circuit. So this nonlinear function will be a function of the load impedance. So here we assume the line impedance is constant. So this line impedance doesn't change. So ES divided by the line impedance is short circuit, which means if the load impedance is 0, the maximal current will be a short circuit current. Okay, so our goal is to figure out the relationship between the VR and the PR. VR is equal to the load impedance multiplied by current. PR is equal to VR multiplied by current multiplied by cosine phi, which is power factor. Then we just plug in the formula of current. So we'll have those two formulas, right, to calculate the V and P. So by plugging different value of load impedance into F, and we can calculate the values of voltage and active power. So for instance, we can take some typical value. Let's see, the power factor angle is 18 degrees. Line impedance angle is about 84 degrees. So the IC just short circuit current. So we can draw how the voltage, active power, and the current change with the load impedance. So X is actually the ratio of the line impedance to the load impedance. So when load impedance decreases, the ratio will increase. So this is the direction of the load increase. This is the direction of load impedance decreases. Okay. So there's some critical value when the line impedance is equal to the load impedance. So that make one of the three curves change the slope. So this curve is actually the current, the ratio of the current to the short circuit current. So this current is keep growing when you decrease the load impedance, because your total impedance is decreasing, right, monotonically. So this current will be growing, and also the voltage of the load is also declining monotonically, but only the curve for IT power, the first increase, then decrease. So that creates a very clear boundary between the two states. So that boundary will have the load impedance equal to line impedance. So now using this figure, we can try to explain how voltage collapse happens on the system. Voltage stability depends on the load dynamics and control. It doesn't depend on generator. It depends on how the load area try to maintain the voltage. So voltage collapse happens when the load control fails to maintain the load power at low voltage, and its attempt leads to voltage reduction and consequently a further decrease in power. So what does this sentence mean? Because there are many dynamic load controllers, such as the thermostat load, like control the thermostat load. Remember in the load modeling session, we introduced for the heater, if you add a thermostatic controller, so when the voltage decrease, you can increase the time duration of the heater, right, to maintain the room at the same temperature. So for short time frame, that heater is impedance load because that mainly does resistance. But over longer time frame, that heater load can behave like constant power load. So why can it be a constant power? Even the voltage decrease because that the controller is able to adjust the impedance. So when the voltage decrease, it can decrease the impedance, increase the load, and make the total power even at lower voltage still be same. Okay, so that's load controller. That's all dynamics on the load, not on the generation side. So if you design such controller based on what's happening on the first state before this, on the left-hand side of this right line, that can successfully maintain the power constant, even the voltage decrease. So when you detect the power become smaller, you decrease the impedance and increase the load, and power will increase, will maintain at a constant value. But when the load is too high and you jump to the right-hand side of the line, and the controller doesn't know what happened because this figure is only available when you have the whole picture of the system. The controller believes you still can decrease the impedance to increase power, but actually fail. The power further decrease. And controller believe it doesn't increase much, it further decrease, and finally that's how the voltage collapse happens. Okay, so to know when the voltage collapse happens, you have to know where this line is, and to know where this line, you have to know this ratio. And this ratio involves both the load impedance, which you know with the load, and also the system, which is the line. But how can load know what happened? So that's a short story on the course of the voltage collapse. So under normal condition, the load impedance is much bigger than line impedance. So that ratio is less than 1. So it will operate in this green zone. You can design the load controller based on the slope, positive slope of the active power. But when the load is too high, this ratio becomes bigger than 1, and that slope becomes negative. All the controller you design for normal condition fail. It doesn't recover the load. It makes system even worse. All right. Does anyone follow me? Yes.
Control is changing the impedance of the load. Is that what it's doing?
The controller by changing the impedance or the overall impedance, that can give you the result that the load can maintain the same. Yeah, this is just one example. Yeah, because think about you just treat, because the actual load can be very complex, but when the if the load connected at one location, and the voltage decrease, and you want to maintain the constant power, the only thing you can do is increase the current. So when you decrease voltage, increase current, which means you try to decrease impedance. Even the load can be very complex, but overall, it's equivalent to decreasing the impedance. Okay, but what this figure tells is the method of decreasing the impedance to maintain the power can be fine, can be successful if you operate in this green zone. But on the red zone, that's totally fail. But the controller doesn't know. Controller just keep doing until pushing the system to the collapse. All right. But in order to know when you move to the right zone, you need to have the whole picture of the entire system, or at least part of majority of the region involved in this event, not just this single load. Let me give you one example of how the load is controlled. So here I use inner load type changing transformer. Inner load type changing transformer is a voltage controller, which means it can control voltage by changing the type position. If you move type up on the secondary side, right, that will make the voltage on the secondary side be higher. But transformer is not a reactive source. It doesn't provide reactive power. So what it does is it takes some reactive power from the primary side and give it to the secondary side. And meanwhile, it also absorbs more reactive power. It's like a broker. We already explained this one. But if we use inner load type changing transformer to control voltage, it can become one of the main causes of voltage collapse because it's not a reactive source. So when the type changer tries to raise the low voltage side, low voltage, basically it needs to absorb more reactive power from the high voltage side. So the control effect actually reduces the load impedance, which is same to what we just described from previous slides. So that if the transformer together with the load operate at highly loaded condition, it doesn't improve the voltage, actually make the voltage even worse. So if the high voltage side doesn't have enough reactive power to support the voltage, this control cannot stop. It will just continue raising the type and finally can cause voltage collapse. So let's explain what happened on this simple system. So first we get rid of transformer and we move everything from a secondary side to the primary side, right? Everybody know the formula. If you move every component from the secondary side to primary side, every impedance or reactance need to be multiplied by the ratio squared. Okay, any voltage need to be multiplied by ratio. Then we can get rid of transformer. So this A will be the ratio for the type position for the transformer to control. That's a control variable. So everything in this box will be treated as load. So this under load type changing transformer together with load is like more like a controllable load. It's controlled by the transformer to try to maintain the constant voltage. The total impedance, we call it ZLD prime, which is equal to A squared, right, multiplied by the magnitude of the impedance, original impedance, including the transformer. So just to make it simple, we consider the line is a lossless line. So the line impedance is 90 degrees, power factor is 1. And the transformer reactance is much smaller than the load impedance. Then we can largely simplify this circuit. And if you can easily get the F function defined, which is the function of the load impedance, is this function. So you see the A is here. Definitely, if there's no transformer, the A is equal to 1. This will be, it will go back to the radio system we talked about in previous slide. And right now, the VR will be the total impedance multiplied by current, which is this one. If we plug in the F function, so it will have this expression. So you see the A is variable. A is only appear here. So this is the voltage you can see from the primary side, okay? But actual voltage of the load is actually can be calculated by this formula. So if you plug in everything, so you have, so now A appear at both items in this under this square root sign. So first one is on the denominator, the second is on the numerator. Okay, so next we want to study when the type is moving, how the voltage is going, is going to change. So if the type move up, we try to increase the voltage on the secondary side. Because here we define the ratio to be the high voltage to low voltage. So A need to decrease, right? If A decrease, so ZLD prime will decrease. Then this A decrease. So this entire denominator will increase, right? So the VR will decrease. And for the VL, it's a little bit tricky because this A will decrease. So this way will, so the first item will increase. Second item will decrease. So whether the entire denominator to be increased or decreased, that really depends, right? So if you're familiar with this type of expression, you know, so if you have variable, you're calculating the sum of two items. So the variable appear in the denominator of the first item, but the numerator of second item. So such expression has minimal value. The minimal value happens when the first item equal to the second item. So which means if this equation is true, so the denominator will have the minimal value. So you can solve this equation. So which means the VL will have a maximum value. So when the VL reaches the maximum value, before it reaches the maximum value, that's how the under load type changing transformer can control the load. But once it passes the maximum value, instead of continue to increase the voltage, actually decrease the voltage. So the power will, the system become even worse. But if this transformer doesn't know, that will cause voltage collapse. So that will explain there will be two possibilities. So if the load is not high, and when you move the type up, the load voltage can be increased. But when the load is very heavy, the load voltage will decrease. But if a transformer doesn't know, it will keep moving up, type up. The voltage will keep decreasing, and finally the system collapse. So if we just give you some idea, if we try two conditions, the first condition is the load impedance is twice of the line impedance. This is represent some like light load condition. So the load impedance far from the line impedance. The second is it just equal to line impedance. So for the first one, you see when the type is move up, the A is a decrease. So we are going to move from the right to left. So the voltage, the load voltage is growing. So this is successful, this control. But when the line impedance become load impedance, the voltage actually is declining. So control will fail. Okay. So in order to prevent the right curve to maintain on the blue curve, we really need to have the entire system model. Then we will know when we need to either stop this control or we just reverse direction. Okay. So that's why typically when the operators or the engineer notice there could be potential voltage collapse, the first thing they need to do is there are number of items, but one of the items will be just disable the type changing transformer before they know what to make sure they have enough margin. When the margin is enough to the stability limit, it's okay to let the type changing transformer work. But if the margin is small, they need to disable the type changing. Now let's talk about the PV curve. That is to model the distance from the operating point to the voltage instability. Okay, so here we need to pick this voltage and this power to make it be a curve. So that is called the PV curve. So In the PV curve, we have X and Y. X will be P, and Y will be V. Okay, but for this case, because we normalize, we use PR divided by the maximal power, and VR divided by the maximum voltage, which is the EMF of the source. So this describes, so when you operate at some very light load condition, the voltage is near 1, okay? But when the load increase, it will move along this curve until reaching this critical point. Once you reach that point, and if you cannot further increase the load, it will quickly decline to very low voltage. So that's what's happening on under the voltage collapse. So voltage collapse, which is a progressive and uncontrollable decline in voltage, typically occurs near that critical point. Some engineers also call that point as nose point or knee point, but it basically means the same thing. So that point is defined at where the slope becomes infinite. But later we'll explain that point is not always the stability limit, depend on system, because here we haven't talked about the load, what load control the system has, right? We only use this system to figure out the maximal power you can deliver to the load. Such phenomenon is often referred to as saddle node bifurcation, it is saddle point bifurcation. Actually, it's saddle node bifurcation. Does voltage collapse always occur when the system passes the critical point? To answer this question, let's first take a look at this system. If this load is an impedance load, definitely I know when the load impedance become equal to the line impedance, that's a maximum power. But if I further decrease the load impedance, the system will move along this curve, right? It doesn't have any stability problem. You won't be able to see voltage collapse. You only see the voltage continuously declining because this system has no load control. That's very simple. It's just the impedance. So when we call it voltage instability, we really mean the instability of some control system. If this load doesn't have any control system, it's just a resistor. It's like adjustable resistor. Yes, the load will increase then decrease, but there's no really instability phenomenon for this system. So the answer is you have to assume some control. So a very strong assumption of control will be constant power load. So constant power load, which means no matter what the voltage is, the power is always exactly this value. But in reality, that will never happen. You have to have some feedback control system based on the real-time voltage current, and you try to adjust maybe internal impedance or do something else to maintain the power. So if it's a constant power load, the answer is yes, the system will have voltage collapse. So let's assume that voltage constant power means there's just vertical line. Vertical line just tell what this constant power is. So at the normal condition, maybe this vertical line. So operate at that point. So when you increase power, this line will move, right? So then at this point, it will tangent to the curve. So if you further increase the power, it will fail, because if you increase the power, there's no intersection. The controller, even they push still to that same direction, but there's no intersection. So there's no operating point for the system to stay there. So system will collapse. Then the controller will fail. So the answer is, if it's constant power load, the voltage will collapse. But if it's the same load as we assumed for this impedance, there's no voltage collapse. because at the beginning, the system can, when it operates at like lie low condition, is quadratic curve going through this origin point. It's like second order function. So when increase load, the curve will change the shape and finally intersect at that critical point. But if you further increase the load, not increase the load, but further doing some control, reducing the impedance, what happens is the line will keep intersecting with the curve. So the load curve and the PV curve always have an intersection point. So which means system can operate there. For constant impedance load, when you increase the changing the impedance, the system doesn't have voltage collapse problem. All right, but if a constant power load, system will collapse at the critical point. For any other type of load, we can always treat that load approximately as some type of maybe ZIP load. For instance, if we ignore dynamic, we can always use some ZIP load to approximate the actual load. So what is ZIP load? ZIP load will be a quadratic function, but not going through this origin. So for instance, the ZIP load can be, let me try. First, let's talk about the constant current load. What is constant current load? Constant current load will be a straight line going through the origin and intersect with this curve. So when constant current load increase the current, so this line will be moving this way. So it also can intersect with the PV curve without voltage collapse. But if it's a general ZIP load will be a general second order function. So which means, for instance, that curve can be like this one. It doesn't start from origin. So when this curve try to increase the line, increase the load, so it will finally tangent to the PV curve at the point, but which can be different from that critical point. Maybe I draw, maybe just make it more clear, like let's see this way. Okay. So when you try to increase the load in that direction, so finally tangent to the PV curve at point, but that is under the critical point. That is the actual voltage collapse point. Okay. So if you have this load, when you increases the loading value, you will observe voltage collapse at that purple tangent point, not that critical point. The critical point is only for constant power load. But because in reality, usually we don't have very accurate knowledge about the load model. We don't really know what exactly the current system, the load model is at this location. So to be safe, usually we just assume constant power load, because constant power load is the most conservative condition. Because any other load may have voltage collapse after this critical load. So usually engineer just use constant power load. And when they use power flow model to solve the voltage at different loading condition, in power flow model, every load bus is treated as constant power, constant P and Q, right? So when you increase the P and Q, you actually assume each load to be a constant power load. So your power flow cannot be solved. That what happens is the system will reach a critical point at some areas, at some buses. Okay, any question? All right, so next we can visualize the PV curve for different power factors. So for this example, we assume power factor angle is 18 degree. 18 degree, cosine 18 degree is pretty close to 1. Power factor cosine 18 degrees is pretty close to 1. It's a very high power factor and high lagging power factor. But if we assume lagging or leading power factor, so we can draw many PV curves. So they can have very different shapes. Okay, for instance, this curve is like power factor 1. The critical voltage, so this curve actually connect all the critical points. on each PV curve. You see when you change the power factor, the critical point also can move. So when power factor is equal to 1, and this critical point is at about 0.6 per unit. But when the power factor further increase, actually we should say become leading power factor, which means the load doesn't consume reactive power. It has internal reactive source, and the power factor become leading. You see this critical point will move up. So when it become the power factor of 0.9 leading power factor, this critical point is close to 0.9. So what this one tells is it's not safe to use voltage magnitude as indicator for voltage instability, because if your system is operating at leading power factor, that critical point can be close to normal voltage. So if you think about more extreme case, has leading power factor, very leading power factor, the critical point can be even higher than 1.0, theoretically speaking. Okay. So for such area, the voltage collapse can happen more easily, even before the voltage decline. It can happen near some normal voltage. So we have to have this curve and identify the critical point, then measure the distance from your current point operating condition to that point. That really tells the margin. So it's not safe just to compare. Maybe let's use 0.9 as 0.8 as threshold. If my current voltage is 0.9, I have a 0.1 margin, but that's not safe because the critical voltage can be even higher than 0.9. So always maintain high voltages cannot prevent voltage instability. Another possibility is what if the power factor suddenly change in that load area? So earlier I operate at that point. So this point corresponds to a 1.0 power factor. So I have a large distance to the critical point, right? So I'm safe away from the voltage instability. But what if that load area has suddenly increased the reactive load? The power factor will change. It will suddenly change to a low power factor. So that point will move to this curve. But for this curve, the distance can be very small, right? It's very close. So when you draw such PV curve, not only you need to consider the current power factor, I also need to consider all possibilities the power factor can vary. So you need to visualize the size of the PV curves, and based on how the power factor can change, make sure you always have enough margin to that critical point. Okay, so let's take a look at one example. We try to solve when the voltage collapse can happen for a specific system with specific load model. So this is still that radio system. We give it some value. We assume the voltage source has 1 per unit voltage, line impedance 0.5 per unit, so has no resistance. Power factor 0.97. So we want to draw the PV curves for that load bus, and if we consider a ZIP load. So this P0 depends on the load level. So we can change the P0 until the PV curve and this load curve will become tangent at a certain point. That will be the voltage collapse one. We want to find that point. Okay, so those 3 equations are the ones we need to draw the PV curve. We just change the value of the load impedance ZLD and plug into the F, then plug into the formula for VR and PR. We can draw the PV curve. We call this equation as number 2. So at the node point, the ZLD will be equal to ZLN. we can just simply plug in here 1, right? So then the F will be 2.486. Then we can plug in to the formula for VR and PR. VR will be a 0.634 P per unit. PR will be 0.780. The next, we want to find the tangent point. We just solve equation. There are 4 equations, but we put them together to solve. And we want to find when the equations only have a single solution. So using MATLAB, I didn't solve this analytically. I just used MATLAB by changing the P0 until they become tangent. So tangent point happened here. So at the tangent point, that's lower than the critical point. So critical point has voltage 0.78. The tangent point have 0.771, slightly lower than the critical point. So at that point, if I further increase the load, so then collapse will happen. So that will be the last point the system can operate. So if you start from some initial loading condition, it will follow this curve. It can pass the nose point without issue until this tangent point. Then it won't have any solution. The system will collapse. So the voltage collapse point can be lower than the nose point. So in the homework, you're going to do a similar problem. Okay. All right, next we talk about the mechanism behind the voltage instability. It is actually saddle node bifurcation. Yeah, so they should call saddle node bifurcation, not saddle point bifurcation. I'll explain what saddle or node mean in this case. So we still study this this radio system, but now I make it be a little bit different. You see that on the low side, I don't consider that load to be an impedance. I just treat it as PQ bus. It's just load bus. We don't have to make assumption for the load model. And on the source side, I can treat it as PV bus. It's just source. It can be generator, it can be other source. And so if we use the source as the reference with voltage E and angle equal to 0, and the load will be negative delta. So delta will be the angle for the source leading the load. Okay. So to study the oscillation, so transient stability, if both sides have generators, we can use the power angle curve, right? Using power angle curve, we study the accelerating area and decelerating area. So if the decelerating area is the larger, decelerating area is the larger, the accelerating area of the system has to be stable. For the voltage stability, we're going to use a PV curve. We're going to draw how the voltage change with P. Okay, so next question is, can we combine those two curves into the same chart? The answer is we have to study the relationship between 3 variables. So the 3 variables will be V, P, and delta. Right? This P is the same P. So we have 3 dimensions to visualize what happened for this system. Okay, so and in that visualization, we can integrate the transient stability, voltage stability into the same system. Then we can study how any instability can happen on the system. One way to visualize it, we still use 2-dimensional. Later I will give you some idea about 3 dimensions. So this axis will be, we'll make this one be P. Okay, and the first curve is still PV curve. We simply just move that PV curve here. But for the power angle curve, I turn it by, I first flip to the left and turn by 90 degrees. So it will become this curve. So this curve is from that power angle curve. So which means the X is P, but Y is both V and delta. So when I operate the system at a certain load P, so I'm going to, if I can assume constant power load, I'm going to draw a vertical line at P. So the line will intersect with PV curve and the power angle curve at 2 points. So on the power angle curve, we know there's a one stable equilibrium point and one unstable equilibrium point. So there's a SEP, and another one will be unstable equilibrium point. Okay. So if we visualize in the state space, so there will be a stable equilibrium point. This guy. Oh. So why is this one called stable? Because when I move the system state away from this point, it will come back, because you see the direction of the manifold, it will come in back to this point, but because it is stable. So all the manifold is merging back to this point. So that corresponds to this point and that point. On the PV curve, that has to be this point, because stable equilibrium has high voltage. There's another equilibrium point, which is this right dot. The right dot is a saddle point, because in one direction, it will be stable, but the other direction will be unstable. So if I draw those arrows. So in this direction, if you move away, it won't come back. But in the other direction, in a orthogonal direction, it will come back. So this point is called a saddle point. Saddle point, which means it's like a saddle surface. So in one direction, it can come back, it's the bottom point. But the other direction is actually the highest point. Should be the other way. So that's a saddle point. But for stable equilibrium point, it has to be in all directions, it can come, right? So this is like a stable equilibrium point. This is unstable equilibrium point. A saddle point is just one type of a stable equilibrium, unstable equilibrium point. Definitely you can have some other unstable equilibrium point. In all directions, it's actually leave, but that's another type. But in this specific example, the system has only 2 equilibrium points, and the green one is a stable one, which has high voltage, low angle. And the other one is the red one, has low voltage and high angle. So which means those two actually belong to the same point. And those two belong to the same point. Okay. So if you want to draw this this figure in 3 dimensions, you add another dimension. So that dimension can be, for instance, you can try if you have like P, have V, and there's another angle delta. So if you try just give it many different operating conditions, so you'll be able to visualize those points in these 3 dimensions. All right. So for right now, the system, if it's operated near the stable equilibrium point, and it will there will be a domain of attraction. So if the system move away from the equilibrium point due to a disturbance, it can come back, right? So it stay within this domain of attraction. So there is certain distance between the stable equilibrium and unstable equilibrium. But if the loading increase, if I increase the load, so it still intersect with 2 curves at 2 points. But eventually, when the load reaches the maximum load, there only just one equilibrium point. Those 2 points will merge. So that's called a saddle node bifurcation. So if right now operate at this line, it only intersect with the 2 curves at each curve at just 1 point, which corresponds to this condition. So bifurcation will happen. Bifurcation means if you further increase load, you don't know what's going to happen. There's no equilibrium point at all. So for instance, if you want to further increase load, equilibrium disappear. Okay, that's voltage collapse. So that means the system will suddenly decline the voltage and it will collapse. Okay, so saddle means this unstable equilibrium point. Node means a stable equilibrium point. So saddle node bifurcation means when the saddle and the node merge and disappear. So that will be the mechanism of the voltage instability. So this is an nonlinear phenomenon. It will never happen in any linear system. When you can find the two equilibrium point, one stable, the other unstable, so you'll be able to study the distance between the two equilibrium points. When the distance becomes 0, so that's how the bifurcation happens. So it is not a linear phenomenon. So in theory, voltage instability occurs when the stable equilibrium point merges with the unstable equilibrium point. All the stable equilibrium point just disappear. But in practice, when the stable and unstable equilibrium point become very close, even a small disturbance can trigger instability. But this instability is a transient instability, not voltage instability. So what I mean is, for instance, if right now the distance is not large enough between this stable and unstable equilibrium point. So if you have some disturbance, the trajectory can move outside of this domain of traction. So for instance, so if we use this one, so this is the stable equilibrium point. I'm describing a scenario before they really merge. It just stay very close, which is corresponding to some condition like maybe like this one. So they still have two intersection points, which means they still have non-zero distance, but they stay very close, which means the domain of traction for the stable equilibrium point will be it's very small. Even if you have very small disturbance, the system will move away. But theoretically speaking, this phenomenon is a transient instability, but it's caused as progressionally pushing the stable and unstable equilibrium point together. Even it doesn't cause bifurcation, but it's like a mix of voltage instability and transient instability. But to study this event, you can still use the P-wave curve to study the voltage stability margin. So realistic cases of voltage stability usually involve transient stability. So those two phenomena happen together. It's called transient instability means there's a non-zero domain of traction, but it's the state from outside exit the domain of traction. That's called transient instability. Because the age of domain of traction is determined based on the critical energy function, right? If you define critical energy function, because the domain is very small. Why it becomes small is because of voltage instability. Because you push the load to make the 2 point get to very close, right? Let's just move. When we get to very close, the voltage collapse has not happened. But if there's a small disturbance that push this stable equilibrium, the state exit the domain of traction. So that phenomenon is a transient instability. But to prevent this problem, you need to use voltage stability tools. So there are 2 stages. Okay, the voltage when it decline the voltage following this PV curve, when it becomes too close to the critical point, the final collapse may not only caused by voltage instability itself, maybe caused by transient instability because the two equilibrium point is too close. The distance is not enough to undergo any further disturbance.
So if the domain of traction is really small, I'm calling it a small singular stability. Like the same.
Now, small signal stability is a different story. Small signal stability means you can use a linearized model. It doesn't mean how large or small the disturbance is small. If you use, it's not small signal stability problem. Small signal stability problem mainly concern the damping. Its oscillation is growing or declining, okay, right? But this is definitely not. This is a nonlinear problem. But you can use a linear model to predict either this voltage instability, or maybe in some study also try to do something for transient stability. But that linearization is not based on equilibrium point. It's based on the local condition near the state. Okay. We are going to introduce the model analysis. The model analysis is using linearized power flow equation, but that linearized power flow equation is trying to linearize not at the starting point, right? It's just linearize at step by step following this PV curve to figure out when the eigenvalue become unstable. For this case, the eigenvalue at the beginning, the eigenvalue it basically means the slope of the curve. But eventually, when that slope become infinite, that corresponds to 0 eigenvalue. So that's the stability boundary for voltage. So you can use linearized model. Okay. Yeah.
With small singular stability, we linearized around the equilibrium point, but with transient stability, like we linearized like every step, but with a different function, right?
If you want, you can definitely linearize. Basically, you linearize everywhere in the domain of traction, right? You're talking about if you know what exactly the shape of domain of traction is, you partition the domain of traction into many small pieces. Each piece can be linearized. Yes, definitely, mathematically speaking, you can linearize anything. The question will be how useful that linearization can be. For transient stability, if you already have model, you just go ahead and do a simulation. The simulation tells you exactly the dynamic of the system after any disturbance. If you know the energy function, you just compare energy function to the maximum value you can have. That will tell the distance to the stability boundary. So you don't really need to linearize anything. My point is you don't have to, but if you want to do some research to use the linearization on each piece of domain of traction, you can. Yeah, the question will be what's your goal?
But I mean the backward or forward Euler is also linearized, right?
Euler method linearization at each point, yes. It's based on trajectory. It's like piecewise linearization. Yeah. Yeah. So that's just general mathematical approach to approximate any nonlinear curve. You can approximate it by some like piecewise linear curve, a piecewise quadratic curve, a piecewise low order curve, whatever. Yes. Okay. Any other question? All right, so we will continue on next Tuesday.